Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at determinants and inverses. Now, we've already looked at adding, subtracting, and multiplying matrices, but division is not defined for matrices. You can't divide by a matrix A. So how do we get around that? Well, we can actually multiply by its inverse. And that's a similar thing that you can do with numbers. For example, dividing by 2 is the same as multiplying by a half. Dividing by 3 over 4 is the same as multiplying by 4 over 3. You can switch between multiplication and division basically if you flip these fractions. So note, dividing by 2 is the same as multiplying by half because we say a half is the inverse or multiplicative inverse of 2. The multiplicative inverse is just the number raised to the minus 1. So 2 to the minus 1 is a half. It's no coincidence that multiplying by 3 over 4 is the same as dividing by 4 over 3, because 3 over 4 inverse of that is 4 over 3. The thing about an inverse, the inverse of a number is the number you multiply by to get 1. 2 times a half equals 1. 3/4 times 4 over 3 equals 1. So this is why dividing 3/4 is the same as multiplying by 4 over 3. These two undo each other because these two numbers, when multiplied together, give 1. The reason dividing by 2 and multiplying by a half are the same are because 2 times a half is equal to 1. These two numbers multiply to 1. Now, 1 is a very special number. It is called the multiplicative identity because it preserves identity. When you multiply a number by 1, you don't change its identity. You don't change what it looks like. So we're going to use something similar with matrices. So we're going to look at the matrix equivalent of 1, these things called identity matrices. So identity matrices are always square matrices. They have 1 along their leading diagonal, so every entry on the leading diagonal is equal to 1, and every other entry is equal to 0. So again, these matrices are called identities because they preserve identities. The thing is, though, we do need a different identity matrix for every possible square size. You need a 2 by 2 identity, a 3 by 3 identity, a 4 by 4 identity. There's also 5 by 5, 6 by 6 identities. They always have 1 along the leading diagonal and zeros elsewhere. So the reason that we call it an identity is because if you multiply a matrix by its identity, you don't change the matrix. Now note that matrix multiplication is usually not commutative. If you change the order of the matrices being multiplied, you get a different answer. But it's actually not the case when you're multiplying with the identity matrix. It doesn't matter whether you multiply A by I or I by A. Whether you multiply by I first or second, it doesn't matter. It does not change the identity of the matrix. So just to give you an indication why that is, here we have the 2 by 2 identity matrix times by this vector. So if I multiply together these two, the first entry here, that is in row 1, column 1. Row 1 by column 1 is just 1 times -2 plus 0 times 3, so it's -2. The entry that goes in row 2, column 1, row 2 by column 1, 0 times -2 plus 1 times 3 is 3. Note that if I multiply the identity matrix by this vector, I did not change the vector. That's why it's the identity matrix. So we're going to move on to inverses eventually, but first we need a quick word on determinants. So it turns out that not all matrices are invertible. That's the same for numbers too. The number 0 is not invertible. There is no such thing as 0 to the power of -1. It is undefined. If you put it in your calculator, you will get an error. So just as there is a number that has no inverse, there are matrices that don't have inverses. So how can you tell when a matrix is invertible, when it has an inverse? You do that by calculating this thing called the determinant. So the determinant takes a matrix and returns a scalar. It's like a function. You put a matrix into this machine and it spits out one number. The determinant of a matrix determines whether or not the matrix is invertible. And it's a nice simple rule. If the determinant is non-zero, if it is anything other than 0, then the matrix is invertible. If the determinant is 0, the matrix is not invertible. So calculating the determinant is quite complicated when the size of the matrix is larger. We're just going to look at calculating the determinant of a 2 by 2 matrix. So this has 2 rows and 2 columns. If I call these entries A, B, C, and D, the determinant of the matrix is just AD minus BC. These two multiplied together minus these two multiplied together. So let's look at some examples. So let's look at this matrix B. If I want to calculate its determinant, I just go AD, so that's 3 times negative 2. It's always minus and then BC. So minus negative 3 times 2. So for a 2 by 2 matrix, you multiply the 2 elements on the leading diagonal, and then you multiply the 2 entries off the diagonal, and then subtract them. Now, if I were to put this on my calculator, and you can feel free to do that if you want, then I get 0. The determinant of B is 0. If the determinant of a matrix is 0, we say that the matrix is singular and it has no inverse. You cannot calculate an inverse for a matrix whose determinant is 0. On the other hand, let's look at C. We're now going to calculate the determinant of this matrix C. So it is the 2 elements on the leading diagonal multiplied together. Then I multiply the 2 entries off the diagonal and I subtract. So this is equal to 6 plus 10, it is equal to 16. Now note that these determinants, the number you get has a lot more meaning than we're going to study in the course. All we care about at this stage is that it's not 0. So if you have a matrix and its determinant is not 0, that matrix is invertible. So here C would have an inverse. All right, let's now finally get to calculating the inverse. So here's the formula for a 2 by 2 matrix. If it is invertible, and this is the matrix A that I showed you on the slide before, A inverse is 1 over the determinant times this. So notice that this is the same as matrix A, except you switched the elements on the diagonal and change the sign of the elements off the diagonal. So let's say I have this matrix here, A. First thing you need to do in order to find its inverse, you need to calculate its determinant. So the determinant here is the entries on the leading diagonal multiplied, then you multiply the elements off the diagonal and subtract. So we get 24 minus 22 is equal to 2. So that means that A is invertible because this number is not 0. So the inverse of A is 1 over the determinant. Now what you do with a 2 by 2 matrix, you switch the 2 elements on the leading diagonal and you change the sign of the other 2 elements. So to find what that is, I go a half times each of the elements of the matrix. So half times 4, half times negative 11, half times negative 2, half times 6. So what exactly have we calculated? So the inverse of A, which we denote A to the power of minus 1, is the unique matrix that you can multiply by A to get I. Just like 2 times 2 inverse equals 1, A times A inverse equals I. This is really important because what it does is allow you to undo multiplication. Remember, I told you that we can't divide matrices, but having these inverses allows us to undo multiplication, and this has a lot of uses. For example, you might use a matrix to encode information in computer graphics. Maybe it encodes information about the color of something. If you multiply by the matrix A, you might change the color, and multiplying by A inverse allows you to undo that and change the color back. So that's why inverses are important. They allow us to undo multiplication. So just to show you this, if I take my matrix A, which was 6, 11, 2, 4, and I multiply by A inverse, which I calculated was this, we should get an answer I. So we know that if I multiply together these two matrices, I'm going to get another 2 by 2 matrix. So I need to find entries that go in each of these boxes. So row 1 by column 1, 12 minus 11 equals 1. So row 2 by column 1, negative 33 plus 33, I get 0. Across by down, 4 minus 4 gives me 0. And then across by down, negative 11 plus 12 gives me 1. When you multiply a matrix by its inverse, you get the identity matrix. And this is another one of the uncommon examples where the multiplication is commutative. You can multiply the inverse first or second each time you get I. So if you multiplied by this matrix, you could then multiply by this matrix to undo it and get back to where you started. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.